wait for the... Hello, everybody, and welcome to this week's Astro Coffee Hangout. My name is Tony Darnell from deepastronomy.space, and today is the day for all of you exomoon lovers out there. In almost every hangout that we ever have on exoplanets, there's always a core contingent out there. And you know who I'm talking about, Alexander Reinders and Adam Synergy. You guys are always asking, well, what about exomoons? And these are moons around planets that are around stars, other stars in our galaxy besides the sun. Well, this week we're going to be looking at new research that studies moons like Titan, what they would be like if they were planets in their own right in orbit around sun-like stars. Now, Titan is the second largest moon in our solar system. It's second only to Ganymede, and as Cassini has shown us, it is the only body in our solar system that is capable of sustaining a stable liquid. Now, unfortunately, that liquid is methane, but, you know, what are you going to do? Well, today's guests have been modeling the atmospheres of Titan-like exoplanets, but instead of modeling them as a moon around a gas giant like Saturn, they model the atmospheres as they go around sun-like stars, along with other kinds of stars like K and M-type dwarf stars. So we are live, so please send us your questions and comments via the live chat on YouTube and also the Deep Astronomy Discord server that's on deepastronomy.space/live, or you can also click on the link in the description box that has the Discord link in it as well, and you can interact with us that way, and I'll be taking your questions and your comments that way. Okay, so let me bring everybody up. Today, we have three guests, but let me start with my co-host. Dr. Carol Christian is in the lower left part. Hi, Carol.
Hello, how are you? How is everybody? Yeah. Good to see you all again.
Yeah, it's good.
I'm really happy because it's finally not 38 degrees in Baltimore.
Oh my gosh. I know it's been a really cold winter.
90 degrees on my backpack. So I'm like, yay, we're happy.
even here in Florida, it's been cold. Like it was down to like 60 or something.
Spring is almost here. But anyway, so everybody's happy outside. Yay, it's going to be a good weekend.
Good. Well,
time to talk about exomoons and water. We can think about water instead of ice.
Yes, and liquids. Liquids are good for life. So I keep being told. Okay, my guest today, I'll start with the upper right panel. Her name is Dr. Tiffany Kataria. She's from the Jet Propulsion Laboratory, and she is an expert. She looks at exoplanet atmospheres. And welcome. This is your second one. You were also in the WASP Hangout. You reminded us.
Yeah, I'm a two-timer now.
That's right. You're a veteran. So welcome back.
They invited me back. Yeah.
Because you're awesome. That's why only awesome people get on this hangout. I mean, that's just the way it is. Right next to her is Dr. Peter Gao from UC Berkeley. He's a no, I'm sorry. That's Juan Laura, Dr. Juan Laura from UCLA. Sorry, apologize there. That's he is very interested in Titan planets and specifically atmospheres of some of the bodies in our own solar system. So welcome. And on the lower panel next to Carol is Dr. Peter Gao. He's from UC Berkeley. He is our chemist, so I'm told, and he will tell us all about clouds and hazes, as well as he's going to answer our questions on the commonality of life later on. I'm just kidding. Okay. All right, let's talk about. I can say stuff. So, you guys, by the way, this is an Astro Coffee Hangout. Carol's going to explain more about the spirit of it in a minute, but I always put the links to the papers that we're going to talk about in the description in both the YouTube Hangout and if you're watching this on deepastronomy.space, it's there as well. So click on there. I think one of them is on the not Astrobytes. What's the AAS Nova website, and the other is on IOP Astronomy. So check out the papers and follow along and ask questions to our guests. Okay, let's start with, I'm going to start with you, Juan. We're talking about Titan-like exoplanets in this hangout. This is what this research is all about. But I think we should probably start with a little bit of a summary of Titan. I said that the very briefest of things about it, it's the second largest moon in our solar system. It would be a planet in its own right if it weren't a moon, right? I mean, it's large enough to be a planet, right? So give us
That's
a little bit.
exactly right.
Tell us a little bit about Titan itself, some of the characteristics of the moon.
Yeah, whenever I talk about Titan, I like to start by saying that Titan is actually larger than Mercury. And so in that sense, it's very much a planet that just happens to be orbiting another planet instead of the sun. And when we model Titan, we often neglect Saturn, especially when we model Titan in terms of its climate and its atmosphere, because what is really important there for the circulation, the dynamics of the atmosphere, is obviously the amount of sunlight and the distribution of the sunlight that's received. So really, Saturn has nothing to do with that. Titan just has a slightly more complicated orbit around the sun because Saturn is his host planet. So Titan, in that sense, is very much a planetary body. It's a really fascinating world. It's one of the ocean worlds of the outer solar system, which means that it has an ocean of water underneath an icy crust. But on top of that, it has this incredible atmosphere, which really is the thing that makes me excited about Titan. Its atmosphere is a nitrogen atmosphere like the Earth's. It is higher density and higher pressure than the Earth's atmosphere, despite the fact that Titan is a smaller body than Earth. And as we know, as you mentioned in the introduction, the atmosphere and the surface of Titan support this hydrologic cycle that's based around methane.
Okay, and I'm just, while you're talking, showing this approach of the Huygens probe as it went down to the surface of Titan to show some of the features. I just love that video, so thought I'd show it. Now I know that we don't know a lot about life in the universe. In fact, I've been making a lot of statements recently about how hard it is to make it. But why is Titan-like planets is so interesting to you guys? Is it because of the thick atmosphere of it? Well, actually, let me back up. Let's talk about Titan-like exoplanets. Now, we talked a little bit about Titan itself. It's a moon. It would be a planet in its own right if it were not around Saturn. What are things that you guys are using to define Titan-like? Anyone? What is it because it's got a thick atmosphere? Well, I mean, okay, so I'm just going to say, so it's about the right same size. It's rocky. It's got a thick atmosphere. Anything else?
It has a surface. I think when you say it's rocky, really what matters is that it has a surface. It depends how you're defining rock. In this case, rock is actually water, ice. But you're right. What we care about is the fact that it has a surface plus an atmosphere, which is similar to Earth, but in a very different regime in terms of the fact that it's much farther from the sun than Earth is, and so the temperatures are very different, and the sort of things that go on in the atmosphere are a little bit different for that reason. So
would Titan have pretty much the same characteristics if it was there and out there that distance for the sun, but Saturn wasn't there?
In many ways, yes. There's a question probably Peter can address more, which is the fact that Titan does travel through Saturn's magnetosphere. That probably influences the upper atmosphere of Titan. But for the lower atmosphere, the answer is yes. It really would just be the same type of body.
Mm-hmm.
Yeah, I'd like to comment on that as well. So as one said, because of Titan's passage through the magnetosphere, there's a lot of high energy particles that enter the upper atmosphere. And what the recent research has found is that shower of particles could be very important in forming the thick orangey haze that blanket Titan. So if it did not have that source, that energy source to break up all the molecules in the atmosphere to polymerize and make these giant particles, it could look very different if it weren't going around Saturn.
Oh, so it's because of the interaction with the magnetosphere that's causing all this opacity in the Titan that we have.
So the fraction is complicated. Part of it is certainly due to the particles, the high energy particles that are raining down from Saturn. Another part comes from UV radiation from the sun, which is what we mostly modeled in our paper. So, which one is more important? That really depends on the situation there, and perhaps lab work is necessary to figure that out. But of course, so if Titan was going around just a star, then it'll still have that UV source. And depending on whether it has a magnetic field or not, whether it can protect itself from the star's energetic particles, that's another. I mean, the star is obviously another source of energetic particles, solar wind, for example.
Okay, so tell me about your model. So your paper is on the model, and you basically took Titan, all of the things that make it Titan-like, some of the things we just talked about, dense atmosphere, rocky, liquid stability, I think would be another Titan-like characteristic, right, Juan?
That's right. So the fact that it has in a temperature,
and pressure range.
And pressure range, exactly. The fact that it has an atmosphere puts it in that pressure range, but its distance from the sun puts it in a temperature range where methane is stable, where methane is near its triple
Oh, you just cut out.
point, which means that it can also be in its gaseous form. We don't think there's much ice near the surface, methane ice, but it could certainly be there in the upper atmosphere.
Mm-hmm.
Okay. All right. So you've taken these characteristics of a model planet like Titan, and you've put it in orbit in your simulations, I assume, around sun-like stars and K and M-type dwarfs stars, correct? Okay. Tell us a little bit about. So what's the model? What do you hope? Describe your model first, and then we'll talk about why you did these stars the way you did.
So what we did was to actually the novel thing, I think, is to take two models and combine them. So we did what we call an asynchronous coupling, which means that we combined the two models by feeding the output of one into the other iteratively. Excuse me. And the two models that we were using were a climate model for Titan, for Titan-like exoplanets,
which were gained from Cassini, perhaps, or
right. It's a model that I have been working on for a long time. It has been validated with Cassini measurements.
Okay.
We've been looking at various aspects of the climate system of Titan, looking for, comparing to data from Cassini. And a climate model really is a model of the way the atmosphere behaves in terms of its dynamics, the winds, the temperature structure, the pressure fields, and how they change over time. And we, as I said, we combined that with a photochemistry model for the upper atmosphere, which I'll let Peter discuss. But our approach was to use this combination of models to examine what would happen if you put Titan around different stars, because that's obviously what we're interested in this paper, is trying to distill the effects of the different stellar spectra on the behavior of Titan-like atmospheres.
Okay, and what did you want to talk about your contribution to the model, Peter?
Yeah, sure. So I'm using a photochemical model. So what this model does is it takes into account all the chemical reactions that could potentially go on in this atmosphere, including ones that are just simple reactions where two molecules combine, or three molecules combine to form, say, a new molecule or break up one of those molecules. And another type, which is the actual photochemistry, where individual molecules are destroyed by light, by UV photons. So that usually happens in the upper atmosphere. And that's really where changing the stellar type from, say, a sun-like star to an M dwarf really matters, because of the different amount of UV that is emitted by these stars. So this model, it takes into account all these chemical reactions, and so also takes into account how they are transported in the atmosphere, and the end result is sort of an equilibrium profile of the abundances of each chemical species.
Is Titan's atmosphere, and forgive me, Juan, if you talked about this while I was looking at the live chat earlier when you were describing Titan, the atmosphere of Titan, well, for example, let's go back a minute. The atmosphere of the Earth has these various layers. We have the stratosphere, the ionosphere, we've got an ozone layer. We have all these different layers within our own atmosphere. Does Titan have maybe not the same layer types or even number, but is it layered? Does it have like delineations in its atmosphere as you go higher from the surface?
Absolutely. And that's another key feature of interest. I mean, most atmospheres that are thick enough really have what we refer to as a troposphere, which basically means the weather layer near the surface, or in the case of planets without surfaces, just the deepest layers that are still considered part of the atmosphere. Above that is the stratosphere. And so in that sense, Titan is similar to the Earth. There is a stratosphere as well,
Okay.
which is a layer that's very stable. And the reason Titan has one, the reason Earth has one is primarily because of ozone, as you mentioned. The reason Titan has a stratosphere is because of the haze, actually. So we can discuss that more if you'd like. And above that, there are several other layers. Many are similar to Earth's layers as well. There's a region above the stratosphere. It's called the mesosphere, and above that, there are other layers. We know quite a bit less about those layers in many ways in Titan, and then above that is other relevant layers to the chemistry, the thermosphere, the ionosphere. So the answer to your question is yes.
Okay, good. Well, yeah. So, Tiffany, I want to get you in on this a little bit here and ask you about planetary or exoplanet atmospheres in general. You study the topic, and I think with a wider net than just a Titan-like atmosphere. How weird is this atmosphere? Do you think compared to? I mean, what's the most common type of exoplanet atmosphere in your estimation?
So I guess my primary focus has been on the giant planet atmosphere. So the Jupiter,
so like gas
Saturn-like
giants and stuff.
atmospheres. Yeah. So the last Astro Coffee that I was on.
Mhm.
In fact, this is actually relevant to this preceding discussion is very relevant to the last Astro Coffee I was on, which was about the first detection of a stratosphere in an exoplanet. And so this was in the case of a giant planet. So in fact, the same extensions that Juan was describing are prominent within exoplanets, and we're continuing to search for stratospheres and the causes of those stratospheres in Jupiter-like exoplanets and further.
Okay.
Oh, also remind us about what the definition of a stratosphere.
That's good.
Sure. I guess fundamentally, the stratosphere is where the region of the atmosphere where the temperature is increasing with height or altitude.
Instead of
So
what
that's
you would
caused by
expect
various
as you
things,
go higher and
Juan was mentioning.
Yeah.
Okay, Carol. Well, this is a good chance to take a break and remind everybody they are watching an Astro Coffee Hangout. Maybe you could talk a little bit about our sponsors and what we're hoping to do.
Sure. So our sponsors are the American Astronomical Society, which is a society, obviously, of professional society of astronomers, and the other is the American Astronautical Society, which astronomers belong to as well, but also engineers. So it's kind of a meshing of astronomy and engineering. And the idea is, we do science, but we need the engineering development for our instruments and observatories. And on the engineering side, engineers like to have practical applications for the things that they create and design. So and a lot of us are involved, there's all kinds of careers in astronomy and aeronautics that mesh well together. And so these two professional organizations have agreed to support us and the Hangouts, which are very informal chats, like a science coffee in our departments. And but we have the researchers live to talk about their research and what they're doing, either theoretical models or how that compares to observations and how those observations are taken to test the models, because we need the models, engineering, and data.
Yes, and I just cannot thank enough the American Astronomical Society for the opportunity to be able to present the research of its memberships and for supporting these hangouts to get them to you guys so that you guys can learn about the latest astronomy research and discoveries that are happening within their membership. So I want to thank them very much for doing that.
And I will say the American Astronomical Society is also very interested in assisting with career development. It's not just everybody's going to be a PhD astronomer, but there are many careers that are in astronomy, but we need all different kinds of talents to contribute to the research.
We need to have a hangout on just that
figure out
topic.
Stuff about the universe. So
yeah, we need to have a hangout on just that topic, don't you think, Carol? It'd be great to just talk with astronomers about what it's like to, what are the different kind of jobs out there? What do you need? I've talked about it in my vlog, but it's a good. I think it'd be a good hangout to have with professional astronomers and people in the field, engineers too. So, good. Okay. Well, all right. Let's get back to your model. So you've told us a little bit about what you're doing, and you've learned some stuff from Cassini that were inputs into your model, Juan, and then Peter comes along. He had some upper atmosphere stuff, and you guys didn't decide to put this model in orbit around different kinds of stars. And well, what happened?
So as I was saying earlier, the purpose of doing that was to try to understand how the atmosphere would react to the different spectra. So these different stars put out light in different wavelengths. So obviously sun-like stars are more yellow than there are the K dwarfs, which are basically more orange, and then the M dwarfs, which are red. And there's a huge variation within them, but we picked out 3 examples from that spectrum to look at how the type of light that these stars really put out impacts the atmosphere, both from a chemical perspective and also from the dynamical perspective. And of course, the 2 things are linked, which is why we coupled the 2 models together.
And you just looked at their spectra in the different cases, the spectra
right, so
of the atmospheres.
The solar or the stellar light has a particular spectrum in
From
each
sunlight,
case,
right?
and that interacts with the atmosphere depending on the atmospheric composition, the amount of haze that's in the atmosphere, etc. So the atmosphere of Titan is very opaque, as we know. You were showing this nice comparison of the 2 wavelength regions where in one you can see the surface of Titan and the other you cannot. And the reason for that is that the atmosphere absorbs a lot of light in the visible, and so that the energy that light brings is deposited in the atmosphere, and that affects the structure of the atmosphere, the temperature structure, which in turn affects how the winds behave. And where in the atmosphere, at what level that energy is deposited depends on the wavelength of the light. So redder light happens to penetrate deeper in. And the reason for that is that the haze, Titan's haze, absorbs much better at bluer wavelengths. So bluer light is absorbed more easily in the upper atmosphere. But there are also molecules that are very important for the interaction of light. Different molecules like ethane and hydrogen cyanide, et cetera. And maybe again, Peter can comment here, but that's the reason to understand how the chemistry is behaving, because there's the feedback between how chemistry reacts to the wavelengths of light, and then how that then impacts the temperature structure of the atmosphere.
How accurate are your models of the stars going into the model of the Titan atmosphere? Because with Sun, for example, it was not the same level of activity as it what life cycle of the star did you pick? Did you pick midlife? And if you did, then why that and not some of the earlier life cycles of the stars? Like, I think, if I'm not mistaken, the Sun was much more active earlier in its life than it is now. It was also, I think, bigger. And
M stars are quite.
And I was getting and these things are a mother in their early lives, right? I mean, they are throwing out flares and all kinds of crap. So where would you pick in your life cycle of the star to input into your atmosphere? Go ahead, Peter.
Yeah, so we kind of just went for standard versions of these stars. The source, I mean, they're not models. They're actually, they're part model, part observation. So for the Sun, we just picked sort of an averaged Sun spectra. For the K and M dwarfs, we went with results of the muscle survey by Kevin France over at UC Boulder. And
yay, my old alma mater. Sorry, I had to do that.
All right. All right. So he has a Hubble Space Telescope. He uses Hubble Space Telescope to observe these stars and measure their spectra at short wavelengths. So most in the UV, and for kind of longer wavelengths, they have a model for that that's well tested. It's called the Phoenix model. And for even shorter wavelengths, I believe they do scaling laws, because at X-rays, for example, you can't actually see through the universe very well because of absorption. But so a good chunk, at least a good chunk of what we use were actual. and K dwarfs.
Okay. All right.
I
and the reason
have a question actually, is that in your model you were talking about also about circulation. So circulation has something to do with atmospheric structure as well, right?
Absolutely. So the circulation is basically how the atmosphere reacts to the input of energy. So energy is deposited at low latitudes. We in this case we considered planets that didn't have an obliquity. So there was no tilt of those planets with relation to their orbital plane, which means that most of the sunlight was absorbed at low latitudes in these planets, and a lot of the high latitudes basically got only a very little amounts of sunlight. And what that does is it produces an imbalance between the latitudes in terms of energy that's deposited. So the way the atmosphere reacts to that is by developing the circulation that transports heat and tries to fill in or tries to erase that enormous temperature contrast that develops. So that's where the circulation is important. And of course, the circulation also transports the different chemical species, et cetera. I just want to jump in about the point that Peter was making previously. We selected to use observations of these stars precisely for the reason that you're pointing out, which is that M dwarfs are very active. So we actually chose an M dwarf that is not as active, but it's still a realistic star. So so we are ignoring the sort of the early type super active stars, at least for now. But we tried not to be overly simplistic and overly optimistic in the amount of, especially low, the short wavelength, high energy light that these stars are putting out.
Okay. Well, so what's the punchline? How did Titan stand up to these various stars? Was it happy being around the sun-like star, and was it trashed by the M dwarf, or what? How did it do?
Well, there's a number of answers, and we can all maybe say something. But to me, the interesting result was that Titan stands up very well and is very Titan-like in all cases.
It's hard to shake its
It's a good
Titanness,
thing.
isn't it? That's a pretty
Yeah,
robust
it's a good
feature.
thing.
It's a robust thing, but I think it's an exciting result because it means that if we find something that looks kind of like Titan around another star, we can perhaps be more confident in saying it actually is a bit like Titan. And what I mean by that is that we observe basically. I mean, we don't really have any hope of observing Titan around other solar systems yet. But if we, when we get to that capability, or maybe we see slightly larger planets that are similar. If we see the type of spectrum from say reflectance or emission spectrum from these planets that looks like the Titan spectrum, then we may have a pretty good indication that it actually looks a lot like Titan. I think that's an exciting result. I was kind of surprised by that. I thought the influence of the stellar type would have maybe a larger impact. But the photochemistry is really where most of it happens. So again, I'm going to defer to Peter on that one.
Yeah, so I think this also goes back to the original question of what is Titan like, and I like to frame it sort of as a question of what's Titan like versus Earth like, or Mars like, or Venus like, right? So Titan is kind of unique in the solar system as being sort of a small body with an atmosphere, but that atmosphere, unlike the ones here and on Mars and on Venus, is not very oxidized, very reduced. So it's a lot of hydrogen species in there, whereas for Earth and Mars and Venus, it's oxidized. There's a lot of oxygen species. Of course, on Earth, there's oxygen. But on both Venus and Mars, it's CO2 dominant atmospheres. So the chemistry of Titan in that sense is very different because, oxygen dominated atmospheres, oxygen dominated chemistry is different from hydrogen dominated chemistry, in this case, methane dominated. So the chemistry itself, it was a little bit different. For the M dwarf and K dwarf cases, the incoming UV radiation was at a much higher level. And so you get a lot more destruction of methane and nitrogen in the upper atmosphere. But the funny thing is a lot of these chemical schemes are in cycles. So if you sort of short out a cycle, there might be part of another cycle that kind of takes over and continues that that cycle. So while we did see changes in the abundances of some of these more important and more abundant stuff like acetylene and ethane and stuff like that, it wasn't that different. And I think the really interesting thing we found is that the hazes that form from all of this chemistry may also not be that different either, just because the haze is sort of kind of the ultimate endpoint of a lot of this chemistry. As you break methane down and you kind of grow it out into larger and larger molecules, it'll eventually all go down towards haze. Now, of course, the caveat is that haze formation is very, very uncertain. And there are a lot of, there's some really nice lab experiments showing they can create haze, but the path from methane and nitrogen to that haze is still very unknown. So, sort of, we're using models to sort of speculate on how these haze form, but there is definitely caveats and dangers in that. But that's what science is all about.
Yeah. Okay. All right. Well, Tiffany, let me ask you this. So we have these models that Juan has been working on, and Peter, and they've inputted into using various stellar atmospheres. And I know from before I became a science communicator, I was a software engineer, and my job was to write a lot of code that was helping run these models and things like that. Tell us a little bit about the role of these models versus observations. And the point I'm trying to make here is that we don't have any shortage of models in science. What we have, I think, is a shortage of observations that tell us which of these models to pay attention to. And one of the things you got your eye on are future missions, right? You're looking at TESS, which is being launched next week, JWST, which is coming out 2 years later, other missions. What missions coming up are you most excited about with respect to this model and this science?
I will answer your question second. First, I wanted to speak to, because I really identify with your first point with regards to, the role that models versus observations just generally play. Mm-hmm. And I think these exercises are really important, particularly as we move to, I think a lot of these models do fundamentally track essentially what observations, the fidelity of the observations that we have access to. And so I think in the case of these giant planets, these Jupiter-like planets, we're actually moving from a phase where we're not just stamp collecting, identifying planets anymore. We're really developing a deeper understanding, I guess I should say, I won't be that generous, of these planets that, that we wouldn't have, that didn't really exist even 10 years ago. And so we're at a phase now where we're actually comparing planets to other hot Jupiters within it's their own sample. And so that's a lot of work that I've done understanding hot Jupiters as an ensemble, not just any particular planet. And so I think only now are we really in that phase of comparative exoplanetology for Jupiter-sized planets. And so, but I think our overall sensitivity in terms of finding these planets and further characterizing them is really starting to move into the small planet regime. Planets like GJ1214b, this depending on who you ask, a super Earth or mini Neptune-like planet, that, we have these really exquisite, albeit flat, spectra for, a particular planet that's quite small as compared to some of these hot Jupiters. And so a mission like TESS, the Transiting Exoplanet Survey Satellite, is really going to do a phenomenal job in finding a lot more of these smaller planets, but also planets that are around brighter stars. And so these are the planets that would be more favorable for follow-up observations with facilities like the Hubble Space Telescope and the Spitzer, but ultimately the James Webb Space Telescope and other facilities that might fly in the future. And so I think it's really important to sort of bear in mind, I guess, the heritage that exists for these models, the relationship between models and observations for these larger planets, because if we don't really understand the dynamics, the chemistry, the circulation that's taking place in these larger planets, we won't really have a chance in H of, doing these same sorts of exercises for some of these smaller planets. So we really need to sort of apply those methodologies and have them be very rigorous, I guess, when we progress to smaller planets.
Yeah, and I bring this up, that this is an important point about how science is done, and I'm sure maybe Carol, I might have some comments on this too, is that You know, I used to be, when I was working in the field, it'd be like, oh man, we got another model. Oh God. So now, you know, we got another model to describe the universe, and now we need, or whatever it happens to be. There was never any shortage of modelers and stuff, but what we really needed was some observations to help us go through this and verify. But you know, they're very helpful. I've come to realize over time that they're also really good in helping us interpret what the observations we're getting are. And so it's really an important symbiotic relationship between modelers and data, because they reinforce and build
Precisely
each
what
other.
I call it. Yeah.
Yeah, and I don't know, Carol, do you have any comment on that? You've been in
Yeah.
the field for a long time,
Absolutely.
so.
Well, since my background is observational,
Mine too.
I mean, I agree with you. It's like you take observations, and there's no shortage of theoreticians.
I know, let's beat 'em up.
rising to the challenge of trying to model. But the important thing is that it actually tests the physics, because without the data, I mean, it's fun. Theoretical modeling is great fun. It's fantastic, you know, and you can make up anything you want, any kind of world, and then you can go into the gaming industry and get rich. But if you want to do physics, you actually need data to compare to the theoretical model. And that's very helpful, because it really is a yin and yang. You know, you collect the data, compare it to the model, and then the model is like, okay, we think we've matched that, but guess what else we predicted? You should also see this. Oh, really? So now we have to go back and see if we can see the observed effects. So it's really interesting, leapfrogging to understand in more and more detail how all these kind of things works. And the fact that I found it very interesting that the Titan model was kind of robust against the parent star. You know, it's like there were changes, but it wasn't like, whoa, it's really different with an M star than it is with a solar type star. So that's interesting too, because that means there's a certain physics which is, you know, very, very strong, that is persistent. So I think we obviously need both.
Okay, well, let me
I
get
think if I can just jump in really quickly, I think
No
Carol just hit the nail
defending modelers.
right-
Sorry, we don't want to hear any
right on
offense
the
from
head.
modelers. We've already
No,
trashed you guys.
I'm gonna jump on the bandwagon here. Everything that was said is exactly right, but I think the key here for this particular study is that, you know, a huge part of the scientific method is making predictions. So comparing to
Yeah, absolutely.
is obviously very important. This is how we benchmark the models in the first place, and we now can make predictions, and we've made a prediction. It's perhaps early because we won't get the observations to test it for a long time, but we've made a prediction about what these types of planets may look like around other types of stars, and we'll test that prediction. And you know, if it comes out to be true or close to true, then we'll know that we have the physics and the chemistry right. And if not, then we have to go back to the drawing board. And that's how science advances.
Well, when it comes,
And I just want to make, a little corner of my brain for, you know, 1/10 of 1% of the population. Theory is not fantasy. And, you know, physical theory is not fantasy. It's not just somebody's made up fantasy about how they think things are. The purpose of a theory is to develop an explanation of evidence. And then when you propose the theory, there's additional things that you go out and look for evidence. So this is evidence-based theory. It's not just fantasy. Oh, I think maybe it might be like this. It has to be backed up and also test evidence.
yeah,
For those of you who
well,
use the word theory.
Yeah, very well said. So let me get to I want to get to future missions very briefly, and I want to do that via a question from Andrew Planet, who is always a great resource for questions. Hi, Andrew. It's good to see you again. He was asking the question. I was just thinking that we can detect a planetary wobble around a star, and we can also detect the telltale signature of an exomoon wobbling around it, or can we also detect the telltale signature of an exomoon wobbling around an exoplanet around its star? Now, he's referring to the radial velocity method, which we've talked about before. Planets pull on a star. The spectrum that you take of that star shows a movement in the spectral lines, and the amount of that movement tells you something about the period of the planet as well as the mass of the planet, things like that. So, upcoming mission will be TESS, and TESS is the Transiting Exoplanet Survey Satellite. It finds exoplanets by the transit method, which is where little tiny dips in brightness occur when a planet passes between us and the star. Now, I don't know if you guys know about any future missions that have to do with radial velocity or if we can do that from the ground. But can we detect these wobbles? And by extension, can we also detect the transits of a exomoon or a Titan-like planet with tests? Tiffany? Maybe?
So, so with regards to radial velocity, I can say that most of the efforts to conduct, so I guess perhaps to give you a sense of scale, the sort of percentage detection you would need to detect the wobble of an Earth-like planet around a Sun-like star, I believe is on the order of like single percent. I think it's fairly, maybe, yeah, I think it's fairly small. I think, but when you consider an M dwarf star, which is much smaller, the sort of relative wobble is going to be larger. And so you might be getting away with, they're easier detections to make. So the basic idea for TESS is most of the efforts to measure the subsequent masses then from this wobble are going to be done from the ground. So there are a number of facilities that are coming online over the next 5 to 10 years to follow up these targets. So to then take, because a lot of what happens with, and this was true of Kepler as well, is, you know, you detect these transits, but they can be degenerate with lots of other things. There could be eclipsing binaries, there could be other random spurious objects. So there's a level of vetting that needs to happen essentially to determine that it is in fact a planet and not something else. And so the radial velocity measurements play a huge part in that in terms of actually measuring the masses to say, okay, well, this is more akin to something that's rocky versus something that taken, you know, in combination with the radius measurement to determine that that's in fact a, you know, rocky planet versus a gaseous envelope versus something else. I mean, there are other tests to vet that they're not eclipsing binaries and other things, but this is one piece of the puzzle. And so the same sorts of exercises, the same tests, the same follow-up observations will be conducted for planets that are discovered by TESS. I think one thing that's great about TESS is that as opposed to Kepler was released with these via a cycle. So there was a sort of series of releases of the data, whereas TESS, all of the data becomes public right away. And so it's really up to the entire community to take these targets and follow them up themselves. And so there's been quite an influx of collaboration within the community to kind of coordinate these observations, because there are so many facilities coming online that would, you know, making sure they're covering the parameter space that's more advantageous to that particular telescope or another in terms of their size and the precisions they can achieve and so on and so forth. So yeah, I guess, but towards understanding exomoons, I would imagine it would be hard to detect a wobble of an exomoon, since it's probably a percent of a percent of a percent kind of signal. But certainly from the transit side, there are many teams that are actively searching for transits of exomoons. David Kipping is a scientist that immediately comes to mind. And so there haven't been any sort of confirmed detections. There have been some recent monitorings of some of these nearby moving group stars that seem to exhibit these kind of dust-like trails, these variable signatures that seem to correlate with nothing in particular. They're just sort of random dips in light. And so one of the theories that's been posited for some of these systems are they're in fact ring systems that are sort of passing through and you're detecting that transit. So that's not quite an exomoon, but, you know, you can imagine some of these maybe failed rings that, you know, failed to form moons, right? So so searches like that are also informative.
It seems to me
I also would guess that it would be a little complicated, like if you consider the TRAPPIST system or our system, we've got a whole bunch of planets. So Jupiter and Saturn are going to influence each other more than Io is going to influence Jupiter. So if you're looking at our solar system from afar, you might detect Saturn rather than Io influencing Jupiter. And I'm not even sure you can see a transit of it. So if it's a multi-planet system, boy, you've got a lot of complicated motions there.
You've got your work cut out for you, yeah.
Exactly. Isn't it true that most of the radial velocity measurements are being done by ground-based telescopes, while we rely on the space telescopes like Kepler and those guys to take transit measurements? Isn't that right?
And that's right. But that's not to say that there aren't ground-based efforts to look for transits as well. The GJ1214, for example, the planet I mentioned earlier, was found via a ground-based transit survey, the MERTH survey, the MERTH survey. So that's still ongoing, in fact, and they've actually detected a couple more planets since that initial one. There's also the WASP survey, which is conducted out of Europe, the Wide Angle Search for Planets, I believe is the acronym. And so they have, I think now, facilities both, and those are just like an ensemble of like simple CCD cameras just staring at the sky, taking half-hour, pictures every half hour kind of thing. And so that's, I think they have facilities both now in the north and south. It's SWASP, South WASP. And so they've found a number of planets, many of which, including the one I was on, the last Astro Coffee WASP 121, there are at least 100 planets that they found via this facility. I think they may have even crossed the 200 mark at this point. So that is to say that there are both ground and space-based surveys, but if you really want to get to the precisions where you can try and nail down transits of small planets, you really do want to go to space.
Well, okay, so when it comes to this model then, it seems to me like you guys would be most excited about JWST, am I right? Because it's going to have the capability to actually give you information on the characteristics and the chemistry of these atmospheres. Is that right, Peter, or and Juan?
Yeah, I think that's right.
Because TESS is just going to give you a dip in brightness. That's about it, right? So
I think TESS is exciting. Well, let me put it this way. I don't think TESS may be able to detect the type of planets we've.
Okay.
Oops.
Modeled here, but at the same time, moon candidate type of thing. Can you? I'm sorry. Can you?
You dropped out, and you said that you don't think it will. You don't think TESS will show us, and then you.
I see. Yeah, I don't think TESS is going to be able to detect the type of planet that we've modeled exactly. But at the same time, Titan is an exciting candidate for an exomoon because of its atmosphere. The fact that it's extended means that it's able to block out more light from the star in a transit than, for example, Ganymede would, despite the fact that Ganymede is actually a more massive moon. Okay. But yes, you're right about the composition being more of an attainable goal with something like JWST. The problem there is, of course, that we're going to need previously identified targets for JWST. The James Webb is not going to go looking for planets because it's
just not going to saunter around the sky and look around, right?
No.
And the other thing I would say though is that where one of the directions we want to go with this research is actually to explore similar effects on larger planets, things that may in fact be observable by the James Webb telescope, things perhaps in the super Earth range that we mentioned earlier. So in some senses, this work has applications there as well. So it is a very exciting mission, and hopefully 2 years from now we'll be on the cusp of major discoveries.
Okay. Do you have any comments on that, Peter? Are you caring? Are you caring about JWST, or you don't care?
Oh, I care.
You do care.
I
Okay.
Oh,
okay.
So I mean, JWST, because of its wavelength coverage way out in infrared, it's gonna see if these species exist, if these chemical species exist in these atmospheres, it could potentially see them. And we're, so far we've been working with sort of just this little band around 1.4 microns. That's sort of, the Hubble Wide Field Camera 3 band. It's fairly high precision, but it's such a short little stretch of wavelength. So it can help us detect water, which is nice. And then way out at 3 to 3.6 and 4.5 microns, we have also the Swarm Spitzer bands. And so right now we have this kind of patchwork of wavelength ranges where we can look. And with these wavelength ranges, we can certainly look at water abundance. We can look at actually atomic sodium and atomic potassium abundances, also clouds and haze, love those. But with JWST, because it goes all the way out to 12 microns with fairly high precision, and it actually goes all the way to like 28 microns, but that's a whole other instrument there. You can detect a lot of interesting things like CO and CO2 and maybe even HCN, I think I've seen floating around, and certainly methane if it exists in these atmospheres. So, and you can all do all this essentially with one instrument, or different observational modes, but you can basically have an entire spectra unbroken, which is very exciting. So that perhaps cuts out a lot of the systematics and the data that always plague our analysis.
Oh, good. Well, I know they were getting to a point where you guys said you had to cut out in about 5 minutes or so. So I got to get this in, and I'm going to start with a question from One Plot, who's going, does the modeling of Titan increase the probability of a habitable moon existing
Yay, I was gonna
around
ask the habitable
a
question.
transiting planet? So let's talk about habitability here.
Yay.
Yeah, and with respect to not only Titan, but just about all of these, it's speculation time. And I got 5 minutes before you guys have to go. First of all, what do you guys think about the habitability of Titan? Is there life there? Forget about what kind it is. Is there life on Mars? Do you think it's possible that life could arise on a planet like, or a moon like Titan?
I think if I can jump in, I'm going to hedge a little bit, but the answer is yes, it's possible. We have some indications of the type of chemical components that would make up potential membranes for cells on Titan, for example. These are really exciting results. I'm going to just plug a potential mission, which is Dragonfly, which is in fact the whole idea is.
Oh, yes, right. I've heard about it. That's going to Titan, isn't it?
Well, it's in competition right now, so it's not. It's
yep,
not certain,
I did a Space Fan News on Dragonfly. Yep.
We can't. Yeah. So I just wanted to say that this is a huge question. It's a major open question that we want to address. How habitable is Titan habitable? It's and to answer, once we have an answer to that question, then maybe we can apply it to the exoplanets that we've been discussing.
Okay. Now I know, Tiffany, you're not a specialist in Titan-like planets as much as you are with the bigger planets. So I'm going to expand this question to just life in general. We talked about this before the Hangout. How common do you think life would be on all of these planets, any of these planets? And just give us your opinion. It's okay to have an opinion. Just say what it is, and we won't hold it against you.
I think life is ubiquitous in the galaxy. I think it's just a question of knowing what to look for. I think the challenge with exoplanet observations in the search for life is that we're collecting these global observations of what are very small processes taking place on the surface or in the atmosphere. And so having a intimate understanding of what processes are actually leading to whatever it is we're trying to find in an atmosphere, I think that's an important step that people are continuing to explore. And so I think we don't have the luxury of sending an orbiter or a helicopter or whatever to the atmosphere to really find it out more definitively one way or another. So that's really the challenge.
Peter, do you have some comments?
Oh boy, it's really hard to make a statement on.
Oh, come on. You don't have an opinion on this? I before the Hangout started, I was asking these guys this question, and I said, what do you think Peter would say? And I predicted he'd say we need more observations. And that's just what he said. So, okay, Peter. Okay, well, fine. I get that. I know we need more observations, but you specialize in chemistries of atmospheres. You look at hazes and clouds and photochemistry, all of these things life cares about. So if you want, just say what you think about Titan as a harbor for life. Is it likely to have with its?
I'm not going there.
Okay, the Titan that we know is certainly full of organic molecules, but it's also
the goo,
very,
right?
very
The
cold.
building blocks.
The goo, exactly. The building blocks. So sort of like a prebiotic, like Earth, early Earth and deep freeze,
and very stinky.
And very sticky. And so it's really cold. So any organic chemistry, at least in the ocean, in the methane oceans and lakes, going to be very, very slow. And I guess based on my modeling efforts with clouds and all kinds of other things, there's so many things that goes into habitability. Certainly not just whether water is liquid on the surface. It goes in, whether the atmosphere is just right, the chemistry is just right, whether you have a redox gradient, whether there's energy to drive life, all these things are important. So, with that said, I would say maybe life is not that. Life is rare. I'm going to say it. Life is rare. There you go.
Thank you, Peter. Two of us against the universe. Two of us against the universe. It doesn't have to be inevitable, folks. And there's nothing that says life is inevitable. Just because you have a lot of building blocks doesn't necessarily mean you up pops life. Okay, I know Carl Sagan said that, but I don't happen to agree right now. So way to go, Peter. You and me. Okay. Yeah. So, is it possible, Susan Hunter is asking, is it possible that Titan is a captured exoplanet. Was it captured, do you think, by Saturn?
Almost certainly not. I think all of the indications are that it formed more or less in the cloud of debris that formed Saturn itself. There's evidence from isotopes, et cetera, that Titan belongs to the solar system.
Okay.
And it's hard to imagine Saturn capturing something from the outer solar system as opposed to Jupiter. So that's where I would leave that. I just have to, unfortunately, also say right now that I need to leave. It's been really fun.
Right. Okay.
I
Understood.
appreciate
Thank you.
it very
Yep.
much. So thank you. But
Yep.
and I'll obviously let the others respond. But
Okay.
Great. Thanks for joining.
Yeah, thank you
We're
very much.
glad for your time.
Yep.
Thank you.
And
Thank you
that's
very
Juan
much.
Laura. He's from the UCLA, an astronomer there. Thank you, Dr. Laura, for taking part. See you later.
thank
Yeah.
you very
Okay.
much.
Perfect. Thank
All right.
you.
Cool. All right. Well, theories on how Titan got there? Do you think was it captured, or was it just part of the accretion of all the planets?
I think Juan gave the answer there.
so-
I mean,
sure.
a lot of it comes down to the isotopic signatures, which I'm not too familiar with in terms of the observations that exist. Certainly, they can test, say, the isotopic fractionation of nitrogen in the atmosphere and carbon as well. But in terms of just so one other line of evidence is, this is a bit flimsy, but it's just the ratio of the mass of all the moons of a planet to the mass of the planet itself. If they form kind of together instead of, say, in a giant impact like with Earth, that ratio has a limit. At some point, the tidal forces essentially break the moon apart. It becomes too massive. So Jupiter is 3 or 4 times as massive as Saturn, and it has 4 times as many large moons as Saturn. So that's sort of like another kind of flimsy line of evidence that say that perhaps Titan belongs with Saturn and formed there.
Okay. Well, I'm looking through some of the questions. You guys, we have about 5 minutes. You guys have a question? Oh, here's one from Simon Farmer. Why would we form an opinion about the existence of exolife before observation? I mean, Earth doesn't even have the most liquid water. Hey, come on. Everybody can
Hey,
have an opinion.
because we are who we are,
Yeah,
and
that's
we
right.
like to speculate.
Yeah, I mean,
What fun is it? If we
I
can't-
know. We're sitting here studying these exoplanets. You gotta be doing it for a lot of reasons. Not only just knowing that it's great to understand the characteristics of an atmosphere around a moon like Titan, but how is it like where we live? What would it be like to live there?
But I think it's okay. Seriously, one question I had was related to what we're just talking about is Titan within the habitability zone, the traditional habitability zone of our solar system? And lots of times these objects are challenging our conservative definition of habitability. So if we only go by what we know as Earth with water, we're not going to find very many habitats. But if we expand what we believe is an environment conducive to life, well, maybe we then figure out how we're going to discover that life. But if we're very restrictive, we'll never find the other stuff. That's my opinion.
Okay, very
Yep.
good.
I fully agree with what Carol says. Yeah, I think until we really fundamentally revise what we think we know about life and how it exists and how it evolves. I mean, it's one thing to, form life. It's another thing to actually be in an environment where that life is sustained. And so understanding the temporal nature of life in addition to all of these other factors, I think what Carol said is spot on.
Yeah, the thing that's just driving me nuts is trying to figure out how hard is it to get something that isn't alive into something that is alive. And if that step is hard, then I think we're going to have a hard time finding some life. But anyway, I love talking about it. It's a great topic that I think that we all too often get hung up on. Well, the numbers. Well, there's 1.6 on average planets around every star in our galaxy. That's what Kepler taught us. There's more planets in our galaxy than there are stars. And well, of course, there's hundreds of billions of stars. Of course, there's life in the universe. That's what you say. Makes common sense. Well, not so much. I'm not convinced. Just because you have a lot of possibilities doesn't mean it's an easy thing to do. So, okay. that is it for this hangout. I think we are out of time. I want to thank my guests for their time today. Thank you, Tiffany Kataria and Dr. Peter Gao, for taking time out to talk about this new model of the atmosphere of Titan around other stars like the Sun and K&M type dwarf stars. Next week, we will be having our Future in Space Hangout, where we will have people on the Parker Solar Probe mission talking to us about touching the sun and what they had to do to build a spacecraft that would get that close to the sun without vaporizing. So we'll talk about that next week with Harley Thronson. He'll be with me, and we'll talk about that. Thank you guys so much for taking time.
This was great.
This was a great hangout, and I want to thank all of
you
you guys for watching.
You guys could make it. It was fantastic.
Yes.
Yeah, thanks for having us.
Welcome back, Tiffany.
Anytime. That's right. We're hoping that as you get more models made, more tests run of, maybe do this around a supernova. Maybe do it around Betelgeuse, and let's see what happens with Titan then. I bet it doesn't fare so well then.
So,
first of many.
Give me the spectrum. Give me the spectrum.
Give me a spectrum of that, and I'll be like, okay, let's see how stable Titan is then. Yeah. All right, guys. Thank you all so much for watching.
Okay, thank you.
And
That was great. Thanks.
Bye-bye.
thank you guys for watching. And as